Boa tarde, pessoal. Boa tarde aos cientistas. Meu nome é Marcos Conceição. Eu sou o vice-presidente do capítulo estudantil da EGE, da UFBA. E essa é a nossa primeira sessão da Semana de Geofísica, a 11ª Semana de Geofísica da UFBA. E esse evento é um evento mixto de apresentações, de mini-cursos, discussões, quizzes e muito mais. A gente está oferecendo alguns cursos, eu vou entrar em detalhes sobre eles no final do evento. E esse ano a gente comemora também a terceira edição, o 30º ano do curso de Geofísica da UFBA. E a gente vai produzir uma mesa redonda com os professores da nossa universidade. Então, mantenha os olhos abertos nas nossas páginas sociais. Hoje a gente vai iniciar uma apresentação com a doutora Greta Trisodi, from LSI Lastem. E ela publicou, né, nessa área de monitoramento com eletroresistividade permanente para solução de barragens de rejeito, entre outras coisas, né? Então, eu vou proceder a partir de agora em inglês com a nossa convidada. Hello, geoscientists. My name is Marcos Conceição. I'm the Vice President of the Student Chapter, EAG, at UFBA, my university, the Federal University of Bahia. And this is our opening section on the 11th Geophysics Week by the UFBA Student Chapter. This event is a mixed event of presentations, mini courses, discussions, quiz, and much more. So we're offering some courses. I'm going to talk about them in the end of the presentation. And this year, we also are commemorating the 3rd year of the geophysics course on our university. So we're going to produce a roundtable with the professors from our university. So keep your eyes open on our pages. Today we're going to start our event with a talk by Dr. Greta Tresoldi from LSI Lastem, who has published on a permanent electroresistivity monitoring solution for tailings dams and more. I'm going to introduce Greta before she starts. Greta is a Master of Science in the Environmental Engineer in Geophysics. After 3 years as a university researcher at Politécnico di Milano in the field of applied geophysics for hydrogeological risk reduction, she is now a product manager at LSI Lastem. As an earlier contributor to the Greta system, the innovative resistive emitter for time-lapse analysis by LSI Lastem, as she has been working on the project from its very beginning. So, Greta, if you would like to introduce anything more or start your presentation.
Thank you very much. Thank you very much, Marcos, for the introduction and also for inviting me to this really interesting initiative, this Geophysical Week, and sharing my screen in order to start my presentation.
Okay.
Can you see the screen?
I'll put it here. Okay. You just have to make it full screen now.
Okay, perfect. Thank you very much. So my presentation is about this Greta system. It is a new kind of georesistive emitter to monitor the integrity of any kind of earthen structures. So just a brief introduction to this georesistive emitter for time-lapse analysis. It is a new kind of georesistive emitter that is meant for fixed installation. It is designed and produced by LSI Lastem with the scientific support of Politecnico di Milano. It is obviously based on ERT measurements, so it is a non-invasive device, and it is meant for geoelectrical monitoring. And so through the survey of resistivity sections a long time, it is possible obviously to obtain some really interesting parameters, mainly hydrogeological parameters, for earthen structures. So, for example, water content, voids, or soil compaction. So, it is a permanent geoelectrical monitoring device And as you can see later on, it is meant for large sections of soils. So thanks to the device and also to the cloud software, it is possible to study the evolution of the resistivity sections, and it is possible to follow the processes that are undergoing in the subsoil. So the evolution of water content, triggering of possible infiltration, and also triggering of possible fractures in earth structures. As I said, the system, it is always connected to a cloud software, and it is possible to consult the data, but also to program the system and also to set thresholds in order to transform this system in an early warning system. Here a short video to understand better the technology, and then we can go also through technical specification and also case studies. So this is the acronym of the system. Here an example of how the system can be used, for example, for an earthen dam, so put on the crest in order to monitor the subsoil. Here the system, there is a box where the different modules for the measurements are contained, and the system can be connected to the solar panel or the main grid. There are the different parts: power unit, communication unit, measure unit. And the system is accompanied by two cables with a number of 48 electrodes in order to perform the geoelectrical measurements. So to insert the current, measure the voltage. Also the inversion is done directly on the cloud software. If something is changing, the cloud can send an alarm message. The system can be also easily integrated with different kind of sensors, so for example, meteorological or hydrogeological sensors. This system has a lot of applications, so for example, the earthen dams, failure risk protection, the monitor of levees, or the monitor of earthen embankments, so for example, railways embankments, and also the landslides monitoring. Also, the pollution and landfills monitor can be a really important field, or the precision farming. There we can go through more in deep in the different kind of applications. So the project of the Greta system started more or less 6 years ago with the Politecnico of Milano in a finance project applied to the levees monitoring in order to lower the risk, the hydrogeological risk connected to earthen levees structures. So the ERT measurements can be really, really useful in order to analyze in a non-invasive way the processes that are inside the structure. So it is possible to analyze the subsoil of the dams or levees from the boundaries, and it is also possible with resistivity analysis to provide alert if changes in resistivity happen. This was really, really useful for managing authorities of, for example, canals or rivers, in order also to plan intervention before the collapse. Another field where the system has been tested is the tail dams monitoring. As you obviously know, these kind of structures are really vulnerable to, for example, different seepages inside the structure. So it is really important to monitor these kind of structures, and also to analyze the processes. So I will speak about it later on. We tested the system in one of the largest mines in Chile in 2020. Another field of application that is really promising is the soil contamination and landfills monitoring. As you know, the pollutants have different resistivities from the host soil, So, for example, the leachate has a very low resistivity, while hydrocarbons have a very high resistivity. So the migration of this kind of contaminants can be followed and also prevented using this kind of systems. A really important field of application is, for example, also the monitoring of the geomembrane of landfills in order to understand if there is a fracture inside this protective layer. Another really important field of application is the one of landslides. Obviously, landslides are a really complex phenomena, but most of them are triggered by water infiltration. So having an idea of the path of the seepage or also the accumulation of water in some parts of the landslides can be really useful to understand the processes and also to combine different measurements, obviously, piezometric measurements, inclinometric measurements with resistivity measurements in order to have an extensive series of data to be compared and to be used for models. I don't want to speak a lot about the electrical resistivity tomography. For sure, you know a lot about it. So the insertion of an electric field through the input electrodes and the measurement of the voltage in other electrodes in order to calculate the resistivity value, the apparent resistivity value. Obviously, there is then the need of performing a tomographic inversion of the data. In our case, the Greta system hosts on the cloud software the tomographic inversion procedure that is automatic. And we use for the system the Venner configuration. We decided to use this kind of configuration because it has a really good response in terms of topographic effects. So we use the Greta system along, for example, levees or dams where the 3D effects are really, really high. So we want to minimize this kind of effects, and the Venner configuration is a really good configuration to minimize this kind of effects. This is an image of the system. It is a quite standard system. So it has one box with inside all the modules to perform the measurements. So the signal switching unit, the main processing unit, the signal driving unit, the power unit. Then obviously there is a battery. The battery can be charged by the solar panel. And there is also a communication inside because this is a system meant for monitoring. So it is autonomous and it can work remotely without the human intervention in the site. So it is really, really useful where the system is located, for example, in a remote place. So, for example, a dam or tailing dam in a place where people don't go every single day. So there is the modem router to communicate to the cloud software. The installation of the system can be done in two different ways. So the cables can be installed horizontally or vertically. Speaking about the horizontal installation, two kinds of electrodes can be used. What we test are the plate electrodes. We use a lot the plate electrodes because they provide a good coupling between the electrodes and the ground, and so the quality of the measurements is really good. Obviously, this kind of electrodes can be used for a monitoring period that is quite long, since you need to dig a trench, not really deep, so only, for example, 40 centimeter deep. And so it's really a simple excavation, and then the cables and the electrodes are covered, and the only thing that is visible from the outside is the pole with the box and the solar panel. In this way, the electrodes are also protected they are not on the ground, so people or animals or means of transport cannot damage them. If, for example, a monitoring campaign of 2 weeks, 1 month must be performed, so not a so long or permanent kind of measurements, it is better to use road electrodes. So for temporary horizontal installations, the electrodes are put inside the soil, but the cable remains on the surface. So in a case of monitoring, it is always quite dangerous to leave the cables unattended, also for the passing of means of transports or animals. Both electrodes are made by stainless steel, obviously. Another kind of installation is the vertical one, to be performed in core. In this case, we design this kind of electrodes with 3 different small electrodes. In this case, the cables are different because the first cable has the electrodes starting from the first point, while the second cable has a first part without electrodes and the second with electrodes. Obviously, in this case, what the result is the mean value of the resistivity along depth. Just a quick view of the cloud software. The cloud software allows to visualize the data obtained from the system in real time, but also to set the system and to decide, for example, the frequency of the measurements, and also to set the thresholds for the alarms or different kind of settings. This is the home page. The user can visualize the position of his systems, and there is also a first diagnostic tool, since there is a traffic light indicating if the measurements are performing well, or for example, if there is a problem in the connection. Then the user can access his own system and can visualize the measurements. In this case, we see the inverted resistivity, but it is also possible to control the raw data, also to control all the parameters, so the injected current, the measured voltage, the quality factor of the measurements. Obviously, it is also possible to extract the data from the platform and to perform other kind of calculations outside the software. On the right side, there is a calendar, and the user can compare and control all the measurements done by the system. So it is a really useful tool in order to perform monitoring, to control the processes during time. We are also performing some changes in the platforms, and we are introducing the possibility of visualizing also data coming from other sensors, because we think that the combining of the measurements is the strong points of monitoring. So starting from February, we will implement the possibility of superimpose the piezometric data on the resistivity section, and also to control the meteorological data, since the Greta system can be also equipped with another data logger, and also with the connection to, for example, rainfall, rain gauges, or other kind of meteorological sensors. It will be possible also to control the meteorological data that can influence the measurements directly from this platform. As I said, the user can also compare different data from different days and manually compare them to control the variation over time. in this platform, it is also possible to set thresholds, so the system can perform automatically comparisons in order to alert the user if something is changing through an email. Another important part of the software is the possibility of convert the resistivity images in water content maps. To do so, it is important to calibrate the system. So, as I will show later on, a core is needed in the site. So, taking the core samples in the lab and measuring directly the water content of the samples along depth, it is possible to correlate the resistivity values that came from the Greta system to the water content of the different samples and obtain a curve, obviously an inverse relation between resistivity and water content. Inserting the parameters of this curve, so in this case A and B, in the cloud software, it is possible to obtain directly an estimation of the water content. What we do usually is also to perform some laboratory analysis on the samples. So, for example, granulometric analysis in order to analyze the subsoil of the site. Here I will show you some last improvements of the system we perform while we approach the tailings dams monitoring field, since tailings dams are really harsh environments and they usually have arid soils. We perform some improvements in the systems in order to have always good quality data. So, for example, we tested mesh electrodes because we thought that they could improve the connections between electrodes and soil and can give better data. So we made a test. We installed 11 stainless steel plate electrodes with an electrode distance of 1 meter, always with the banner configuration. We buried the electrodes in a small trench, 20 centimeters deep, and we use a different kind of electrodes. For electrodes from 1 to 5, we use the bigger plate electrodes that you can see in the image, while for electrodes to 6, from 6 to 11, we use the smaller electrodes. We perform a 7-hour experiment measuring contact resistance every hour. But after the first measurement with the plates electrode, we changed the electrode 2 and 3 using mesh electrodes. So we wanted to test this new kind of electrode. Here you can see the different lines that corresponds to the contact resistance a long time during the experiment. Every line is the contact resistance a long time of one electrode, and you can see the zoom of the electrode 2 and 3. You can see that the red point is the first measurements with the mesh electrode. As you can see, the difference between the plate electrodes and the mesh electrodes was not significant. We performed this test on one kind of soil. We want to perform more tests on different kind of soils, but for this kind of soil, we don't consider this kind of electrodes an improvement in the contact resistance test. So we decided to continue using plate electrodes also for the mining environment. Another point is the low-level measurements. We implemented the plus to minus plus method for injection. So we we wanted as an objective to suppress the low frequency variation in background spontaneous potentials. And so we include in the system this new method for injection. So the current injection may consist in a positive injection, a double negative, and finally another positive pulse. So you can see in the graph, so the linear spontaneous potential that is sum on the normal voltage that is measured. So this kind of filter with coefficients 0.25, minus 0.5, and 0.25 can suppress the linear terms of the spontaneous potentials that can be measured in really disturbed environments. Then we implemented also the Focus One protocol for contact resistance. And so we wanted to measure the true single electrode contact resistance and not the couple contact resistance between electrodes. So this kind of measurement is done measuring the resistance between the focus electrode and all the other electrodes connected in parallel. In this way, it is possible to measure the contact resistance of the focus electrode, that is the one that dominates the other resistances. Then we changed the measurement sequence in order to avoid the polarization of electrodes. Since if a couple of electrodes used previously to inject the current is then used to measure the voltage, it is possible to have a polarization of the electrodes and the measurement can be damaged. So we change the scheme of injection in order not to use the same electrodes for injection and then for measurements. Another important point that we introduced directly in the system is the automatic electrode depth compensation. So we changed the geometrical factor of the measurement, the calculation of the apparent resistivity, and we modified it in order to account for the barrel depth of the electrodes. Since we use to bury the electrodes in order not to damage them, we wanted to include this effect directly in the measurements, so using directly a modified geometrical factor. About this point, I will show you a preview of some slides from the next near surface geoscience and engineering that is this month. It will be this month. So I will show you some slides from my colleagues that we produce for this conference. These slides are made by Azadeh Ojat, that is a professor of Politecnico di Milano, and also of Shoaib Baonar University of Kerman. The title of our presentation is Correcting the Effects of Soil Covering Buried Electrodes for Permanent Electrical Resistivity Tomography Monitoring Systems. So in order to create this new geometrical factor for the calculation of resistivity, we studied the optical hypothesis of the image source analogy. So we studied the effect of the layer above the electrodes, starting from the very beginning. So 2 points, one where there is the injection of the current named I, and one where there is the measurements of the voltage named P. So we studied the reflection of the image source, and then we obtain the voltage that is measured with this configuration, with an homogeneous subsoil where these 2 points are set. So this equation with only one point of injection and one point of measurement can be extended to calculate the potential differences between any two desired points. And so we extended this calculation to the Venner configuration with unit electrode spacing named A. And then we can see here a formula that is the ratio between the calculated resistivity without the correction and the resistivity of the soil. We can see that not considering the barrier depth of the electrodes, we can underestimate the real resistivity of the soil. We can see, for example, here two graphs, one on the left for the Venner array with the electrode distance of 1 meter, where we can see that we have on the x-axis the spacing between electrodes. Then, if the electrodes are buried inside a trench that is half meter deep, we can have a decrease in the calculated resistivity of 25% for the spacing of 1 meter. Then we can see that if the spacing between electrodes is bigger, this effect is lower. So we can see that this effect is related only with the first level of measurements. So where the spacing between electrodes is comparable with the barrier depth of the electrodes. But it can introduce a sort of mistake in interpreting the first level of measurements. What we can see is here the percentage changes in resistivity, so in the calculated resistivity with the different spacing between electrodes in respect to the barrel depth. So we can see, for example, that for a ratio between A and H, so between the spacing between electrodes and the barrel depth of 2, we can see that as I said, the variation in the calculation is the 25%. We can see that this error rapidly decreases for larger electrode spacing. So going in depth, so with wider electrode spacings, this error is not so significant. But changing the geometrical factor in the calculation of resistivity on the apparent resistivity, we can eliminate this error and we can perform automatically the inversion without introducing such an error. Here I will speak you about some case studies of the Greta system in different fields of application. So the first case study is the installation of the system on the tailings dam in Chile. The monitoring aim was to monitor the phreatic level through this kind of measurements, so through earthen measurements, below 2 wastewater ponds. So these wastewater ponds were built below the dam, and the problem was to understand if the variation of this level in the ponds will influence the phreatic level. So the study was done by installing for a medium-term campaign, so only 2 weeks each, 2 Greta system profiles, and compare the resistivity data with the piezometric data present on the site. Here you can see some photos of the first profile. So the system was put obviously in the center of the profile. The cables were spaced. The cables had the space between electrodes of 3 meters, and the surface electrodes, the road electrodes, were used because the monitoring campaign lasted only 2 weeks. We can see also the position of the wells in the site. And here we can see also the profile 2. As you can see, the soil was really harsh, really arid, and so we studied a lot the contact resistance, as you can see later on. The problem was the contact resistance between these electrodes and the soil of the mine. You can see that we tested the contact resistance over all the measuring period. In the graph, you can see the number of the electrodes on the x-axis and the contact resistance in 3 different measurements. So the first measurement is the black line. You can see that there is the last part of the profile that was quite bad in terms of contact resistances. After 1 day, we tried to lower the contact resistance with salt water and also hammering the electrodes. The fact then was that there were some rainfalls and the resistivity went really good along all the period of monitoring, and the end part of the profile was more or less like the other part. What we can see is that also the standard deviations of the measurements were really good. We can see a pseudo section of the standard deviation of the measurements during the first day of measurements, the 26th of August. We can see that more or less all the points were under the 0.5%, except for a line of measurement corresponding to the end part of the profile, the worst one, while in the last day of measurements, the 8th of September, the situation was really good. So we obtained a high quality data for all the period. This is a focus only on profile 1, but we had also the other profile 2 for other 2 weeks. What we obtained was an image of the processes in the site, so we can understand also thanks to the piezometric data the position of the groundwater flow, and you can see a great difference between the first part of the section, the shallow one, with high resistivities, and the second part, the deep one, with resistivities around 80 ohm per meters. The aim of this study was also to follow the variation of the water level in the pond compared with the variation of resistivity. I cannot show you all the data, but only a part. We can see the position of the piezometer in the zone and the variation of the resistivity with the boundary between the 2 zones that is going up while the water level is rising, and then also the water level that stays the same, and also the resistivity stays the same from the day before. Another case study that is in reality the first one is the San Giacomo delle Segnate site. Is a site in the northern part of Italy where we tested the ERT technology in order to obtain valuable data in order to understand different kind of seepages in an earthen embankment of an irrigation canal. I can show you different measurements that we perform along 1 year in this earthen embankment from September 2014 to September 2015. As I said, this was the first test in order to understand the feasibility of the system on this kind of application. We can see different sections of resistivity along time, and we can see on the right the height of the water table in the canal, and also an image. So this is an irrigation canal, so the level of the water in the canal varies along the year. So during summer is really high, and during winter is low. We can see, for example, this site was known by the managing authorities of canals because there was a known excavation, a known concentrated seepage. So we can see that from the first image, we can clearly understand where this seepage is, this concentrated seepage is, while after the lowering of the water, the canal, the low resistivity zone is present but not so clear. During the winter, the soil is dry, there is no water, there is no seepage, so the resistivities are higher, while after almost 1 year, with the presence of water in the canal, the concentrated seepage returns. The situation became worse during the month of August, and then the situation is really strange because it seems that the seepage is not present. The fact was that in the exact position of the identification of this concentrated seepage, there was a failure, a partial failure of the levee, and that gives us the proof that the system is really effective in understanding the exact position of concentrated seepage, also in this case 1 year before. So this was the first installation of the Greta system on this embankment. Here you can see the trench, the position of the box inside the trench, and the cables that, in this case, were with an anti-rodent plastic case in order not to be damaged by the rodents present in the site. Another case study is related to a bad event that occurred on December 2017. There was a flood in the northern part of Italy, and two different embankments of this river Parma, Torrente Parma, fell down partially due to concentrated seepage. So you can see that these levees were rebuilt, but obviously with different kind of materials. So we perform some portable measurements in order to understand the situation along a long part of the levee, and we identify really well the new built part that was built with the soil with a high percentage of clay. So there was a quite difficult situation since the old part of the levee has different material compared to the new part. So it will be quite an hazard, for example, with another flood. It can be really risky. So the managing authority for this part of levees decided to put a Greta system inside. In this case, with an electrode distance of 2 meters, so with a total profile length of more or less 100 meters, and a investigation depth of more or less 15 meters. These systems are still working, and they provide daily measurements. Obviously, the frequency of the measurements can be changed. For example, if there is a flood or if there is some risky event. So, in conclusion, this Greta system is an innovative off-the-shelf remote sensing solution for the geoelectrical monitoring of hydrogeological risk. in different fields of application. So we saw the earthen dams field and tailing dams field, levees, earthen embankments monitoring, and also the field of contamination risk protection. It is a totally autonomous system, easy to install, and it does not require particular maintenance. It allows the continuous geoelectrical remote monitoring of large sections of soil, and it can be used also to manage early warnings. So we want to see that is geoelectrical monitoring made easy. Other list of conclusions, the last improvements to the Greta systems resulted in high quality data. We discarded mesh electrodes, but we want to perform more tests. We introduced the plus to minus plus algorithm for more stable data, and also the Focus One protocol to measure the exact contact resistance of each electrode. The sequence was modified in order to avoid the polarization of electrodes, and we implemented also the automatic depth compensation for the calculation of the apparent resistivity. The first installation on the Chilean tailing dam was really successful with good contact resistance a long time and also good quality data. And it was possible also to match piezometric and DRT data. The monitoring sites that we still have on river levees provide good daily data, and they are really help. They help a lot the managing authorities for river and canals, providing information about possible maintenance or also hydrogeological risk protection. So thank you for the attention. If there are some questions.
Oh, Greta, thank you very much for your presentation. It's an honor for us to have such a talented researcher presenting for us today. I myself see many applications for this in Brazil. You may have heard of some tailing dams problems that occurred here in the last years, like from the Brumadinho and Mariana. And actually, at my city, we have a lot of landslides every time it rains strongly. So I see many applications of your contribution to the world. We have some questions here, and I myself have some. So I'll start by Matusada Mais. Oh, he has written in English too. So good afternoon, Greta. Is the system itself capable of checking electrode malfunction over time?
Yes, absolutely. On the platform, it is possible to set the frequency also of contact resistance tests. And the system itself store the data of the contact resistance over time. So, for example, we used to perform weekly contact resistance tests, also because these systems are working remotely. So we cannot go there and control every time the electrodes that are buried. So it is even more difficult to have a control on the electrodes. And for this reason, we introduced the possibility of performing contact resistant tests remotely.
Okay, so he also asks below, how do you see the benefits of the system, the Greta system, to the agriculture, for example?
Okay. Yeah, thank you for the question. We had an experience some years ago about the agriculture, precision agricultures, because the user wanted to control the soil moisture during particular seasons. For if I remember, was the crop agriculture, and this user wanted to quantify or have an estimation of the water content for irrigation. So it was used in these terms.
Okay. So the next question is from Mariana, is by Mariana Sampaio. Good afternoon, Greta. Greta really sounds like a great system and a nice solution. I was curious about how long do you expect the Gretas to require natural maintenance? And she continues, and what are the most common risks that can hinder the full functioning of the device, whether they are electronic or environmental problems?
Thank you, Mariana, for the questions. We proved that more or less the maintenance of the system can be done once per year. The principal maintenance actions that must be done is the control of the battery. If the system is powered by a solar panel. Also, this information is contained in the cloud software, so the user can control the life of the battery. So if he see that the battery is low, it has to go on the site and change it, probably once every 2 years. But once a year, it's useful to go on the site and, for example, clean the solar panel and control if everything is okay. The most common problems can be related, I think, to the power of the system, since the ERT measurements are quite demanding in terms of electricity. And if there is the main grid connection, there is no problem. But obviously, if you have the solar panel, you can't schedule a lot of measurements per day. So if, for example, there is a cloudy period or rainy period, probably the solar panel can not charge the battery. One solution is we provide additional power pack with additional batteries, since this problem of consumption of current is quite important. So we must guarantee the functioning of the system also with rainy period, also with cloudy period. So we can provide this additional battery pack. Another problem can be related to the fact that the system works remotely. So if some people, for example, stole some parts of the system, obviously it can be quite dangerous. So what some users implement is a fence around the system to protect the mechanical part from people that wants to steal some, for example, the solar panel or the battery, or damage the structure.
Did it ever happen before?
No, so far no, fortunately.
Awesome. Okay. Um, linking with this question, I would like to do one of mine. How much infrastructure is needed to install the system?
Sorry, how much?
Infrastructure, like, do you need energy?
Okay.
How in the country, how inside the country we can install
Okay,
this?
the installation does not require particular infrastructure. So, as I said, if you have the main grid on site, it is always better. You don't need, you need, for example, 1 or 2 technicians in order to install the system, and also to, for example, dig the trench. But as you saw from the image, is not such a big deal. It's not really difficult to install the system. So it is important to have the GPRS connection, so the mobile connection for internet, since the system is controlled by the cloud platform. So if internet connection is not present, it can be an issue. The system can be also programmed via a PC on site. but obviously the strong point of the system is the fact that the user can control the measurements and program the measurements remotely.
Okay. Another question is how frequently the acquisitions are made by the system.
The user can decide the frequency and send the configuration to the device. What we suggest is one measurement per day, since the processes that we are studying are not so fast. One measurement per day is enough, but obviously if the situation is changing and, for example, the user see that something is changing in the soil, he can decide to increase the frequency, and if the system is powered via the main grid, there is no problem. He can do also one measurements per hour, for example.
I get it. Oh, it's very nice to hear that. Currently, does the Greta system is it able to invert data acquired on high slope zones?
Yes, the fact is that the electrodes must be installed on a plane, so we don't want to have topographical variations on the position of electrodes. So if, for example, there is a really difficult topographic situation, we are not happy. We don't want to invert this kind of data, providing bad data. So we always tell the client, the user, to prepare a quite plain situation, also with slope, but a linear slope, not with difference in the height of the electrodes.
I understand. Okay. And lastly, do you see any applications of the system for water exploitation monitoring? Like for
Yes,
control?
absolutely. Since the saturated soil can be easily recognized by the ERT measurements, the system can be used to monitor, for example, the exploitation of the water resource. The limit of the system is that the maximum length between electrode, since it is an autonomous system and it has to not use too much current, the maximum distance between electrodes is more or less 3 meters. So the maximum depth with 3 meters is around 22 meters. So it is a system that is meant for quite superficial analysis, not, for example, for investigations, for oil investigation, but if the water table is quite superficial and not so deep, the system can be really useful to follow the processes in the subsoil.
Okay, so thank you. Mateus Adames said, thank you for the answers and for the awesome presentation.
Thank you, Matteo.
Mariano Sampaio, thank you so much. Congrats for the presentation.
Thank
Greta, thank you again. It's very nice to have you here. Do you want to talk about LSI? Introduce anything? Or?
Yes, just a brief introduction about the company to close this interesting meeting with you. And so LSI is an Italian company. It is focused on environmental monitoring systems, mainly for physical environmental parameters, so meteorological parameters, also for parameters, for example, in landfills, also air parameters or indoor parameters. So we design, produce, and sell sensors, data loggers, software to monitor the environment. The company is really old, since we are on the market from the mid-90s. And we provide also different kind of services, so installation, technical support. You can visit our website, that is lsi-lastem.com.
Okay. Thank you.
Thank you, Marcos.
Just to so that people know, we are going to offer some courses along with these presentations. The first courses is on Os's montage by Sequent. The second is a course on GPU programming with CUDA by NVIDIA. And the third course on Google Earth Engine by Rodrigo Routo from CPRM. He has previously presented for us. So these courses are going to be offered by a symbolic price. So it's meant for students, and you can access these links or subscribe to them in our pages, social pages. Thank you again, Greta. Thank you for the people who are listening to us, and see you.
Thank you very much. Have a nice geophysical week. Bye-bye.
Bye-bye.